Morning, everyone. So this last part in the acid-base chapter here is more like a nature of science kind of connection. We've been looking at different definitions of acids and bases. We mainly have been dealing with Bronsted-Lowry ones, which basically involve a one-proton transfer. We've studied how we do calculations for strong acids, weak acids. For weak things, we have to do ice tables. We looked at titration curves and try to find an unknown concentration. Looked at buffer systems that can end up shifting left and shifting right. And now what we're going to do here is we're just going to generalize and we're going to say where are some places that we actually see acids in nature. What should come to mind here is actually acid deposition or acid rain. What are sort of some of the concerns around acid rain here? What's some of the chemistry behind it? And what are some ways we can actually address the issue of this acid deposition? So let's just finish through this last section here. In general, this is called acid deposition. You may remember from our periodicity chapter here, we actually looked at our period 3 oxides. In general, if I have acidic oxides are typically going to be covalent oxides, individual compounds here. Usually we refer to them as SOx and NOx. Basically, it's sulfur oxides, SO, SO2, S2O4, things like that, NO2, NO3, like that. These ones here as non-metal oxides, they end up forming acidic solutions. So in the atmosphere, they end up interacting with the water as rainwater forms in the clouds. And basically, our rain, as we're going to see, is already naturally acidic because of carbon dioxide. But some of these other gases here are sort of byproducts of industrial processes here. This is actually causing our rain to rain down actually more acidic than normal. And that's what we refer to as acid rain. So acid deposition is a more generic term here. Acid deposition is the process where acid forming pollutants deposit, they fall onto the Earth's surface. So while we will be looking at acid rain in specific later on, acid deposition is a little bit more general. Make sure you know this cause here. The cause is by these industrial byproducts, some combinations of sulfur oxides, nitrogen oxides. These are all covalent oxides. Some ways that acid deposition can affect the environment. It can lead to deforestation, leaching of minerals. It can cause for the reduction of pH. At first, you may look at that and be like, oh, doesn't that mean more basic? Well, remember, pH getting smaller, pH 7 to 6 to 5 to 4. This right here is actually getting more acidic, as you might imagine if more acids are actually hitting the ground. Some of this will actually run off into lakes and rivers and affect a lot of marine creatures. It has corrosion on materials. Limestone is a really common one here. Limestone is actually made out of calcium carbonate. We've seen a reaction. Basically, carbonates are actually reactive with acids, and acids will basically eat away at limestones. In sort of caves with a lot of limestone, this is actually where you end up getting those sort of stalactite, stalagmite. Basically, what happens is water sort of runs off on the roof here. The crystals are sort of crystallized on the top. We get these little protrusions from the top. Sometimes the rainwater actually drops to the bottom and it ends up leaving deposits down this way. Sometimes you end up getting columns of them. We end up getting these interesting structures here in caves, but especially if I have like a marble statue or a limestone statue, the acid is just going to start eating away at it. Right? So for starters, I want to just qualify here, what is not acid rain? So our rain is naturally acidic, so this is an important note, because CO2 is a really prevalent gas in our atmosphere. CO2, like our SOx and NOx, are also non-metal oxides. It is going to end up forming an acid in solution. So basically we have CO2, this is gaseous. It's going to run into our, let's say, our neutral rainwater pH at 7 at 25 degrees. This one here is at first going to end up forming carbonic acid. Right? Carbonic acid here. While there is some talk about does this acid actually exist, regardless whether this chemical can form or not, this one here, as in Bronsted-Lowry acid, this one can actually donate a proton and end up becoming HCO3 minus. The HCO3 minus, it still has a proton to give up. This HCO3 minus can also, in turn, give up another H plus and form CO3 2 minus. So basically, our rainwater, right? You can imagine we have our clouds. It was supposed to be just pure water, just pure H2O, but interacting with the carbon dioxide that is naturally there, it forms this carbonic acid, and eventually it ends up leaching this H plus into solution. so carbonic acid. Our natural rainwater, because of this, is roughly about 5.6. Okay, remember we're on a logarithmic scale here. Every step is sort of 10 times more intense than the one before it. Because of that, rain that's between a pH of 5.6 to what should be 7 is not considered acid rain. Okay, we're going to actually reserve that acid rain term for what's coming up here. Rain is already naturally acidic because of this carbonic acid. Okay. Just as we work our way towards acid rain here, there's two forms of this deposition in general. There can be a wet deposition, so acid rain, what's coming up here will be an example, right? It's wet, it's in the liquid form. It could be in the form of fog or condensation, acidic snow or hail, dew, okay? All sorts of different sort of water hitting our environment. Or it could be a dry deposition here. It could be just the acidic gases themselves. Right? They're actually not watering down as liquid here. It could be particulates. Particulates, sometimes they actually scatter light in our atmosphere, so that actually causes other environmental features. But our main focus here is the acid rain problem. So based on natural rainwater here being already a pH of 5.6, we're going to now qualify rain with a pH something less than 5.6. This is what's considered acid rain. The lower the pH is due to not just the carbonic acid that's already naturally there, it's due to our industrial gases that we tossed in. So our industrial gases like, we'll just say SOx in general, SO2, SO3, these ones here through the contact process. If you remember back in our equilibrium chapter here, upon touching water, non-metal oxides, they interact with the water in the clouds and they end up forming things like sulfuric acid. Nitrous gases end up forming HNO3. So let me just rehash for you how come there's so much of this SOx in the atmosphere. We actually burn a lot of coal for our energy. Coal is just deposits of carbon. One common impurity for coal here is actually sulfur. So sulfur starts off in the solid form. It first gets combusted. Usually for combustion we end up with CO2 and water. There is no carbon source. This is just a sulfur impurity here. This ends up oxidizing. So O2 is a gas. That's where we actually end up getting SO2 gas. 2SO2 gas here can then react with oxygen, can actually oxidize further to become 2SO3 gas. This is part of the contact process. You should remember it's a vanadium oxide. That's the catalyst for this reaction. And then what ends up happening is because these ones here are both non-metal oxides, both of these, when they are in the presence of water, SO2 would end up forming sulfurous acid, H2SO3, and then if I react it with water for SO3, this is actually going to become SO4, H2SO4. It's going to be like a fancy synthesis reaction here. You do want to watch the balancing there, but non-metal oxide ends up forming these acids. Just a quick comment on naming here. No problem if you call this one here sulfuric acid. Right? This one here comes from sulfate, ATE. SO3 is actually coming from sulfite. We would have actually called this sulfurous acid. We're going to step into our redox chapter very shortly here. What redox does for us here is to identify which things actually gain electrons and lose electrons. It actually says, although this compound, the polyatomic is actually covalently bonded, the ionic attraction is between the positive and the negative bit here. This is a compound that contains both ionic and covalent. What we're going to do is we're going to write what's called the oxidation state. The oxidation state actually just assumes the entire thing is ionic. So let's just think for a second here. Assume that it's completely ionic. Assume that there's actually no covalent bonds. What we can do is we can actually find the oxidation state or the oxidation number. It's like how charged it is right now, so that over the course of the reaction, has it picked up electrons or has it lost electrons? So if I try to do the math here, hydrogen is usually a +1. Oxygen here is usually a -2. I want to know what charge sulfur has to make sure that the charges cancel out. The math that I'm thinking here is 2 plus the 1 from the hydrogen plus whatever sulfur is plus 4 times whatever oxygen is. Each of them is -2. They all end up giving you no charge overall. What does sulfur have to be? Sulfur, you should be able to find for me, it's +6. And this is where they're super particular. It has to be the sign first and then the number. They're actually going to mark you wrong if you just put 6+. That's why some textbooks will actually call this one here sulfuric 6 acid. Usually we don't get those Roman numerals unless it's a multivalent metal. You can have multiple charges. In this case here, it's actually identifying for you the oxidation state, the oxidation number. It's like the sulfur is a +6. What about the H2SO3? I want to get you enough practice here that you can just go, well, H is +1, there's 2 of them +2. Each oxygen is -2, there's 3 of them -6. Sulfur, with the 2 here, minus the 6 here, has to give you over a charge of 0. So the sulfur here is actually 4. So in textbooks, you'll sometimes see this written as still sulfuric. They don't actually use the us acid form, but they'll actually instead call it sulfuric 4 acid, just to identify the oxidation state, just to make sure it's signed first, then the number. So that talks about how industrial gases, SO2, SO3s, they leach into our atmosphere. Those non-metal oxides interacting with water end up raining down. Our rainwater pushes it lower than pH 5.6, and that's called acid rain. If you flip over the back here, we have also nitrogen sources as well, NO2s, N2O, things like that. They're going to end up forming nitrous acid and nitric acid. I can show you some of these reactions here. We start off with just N2, right, a primary component in our air. This one here gets burned, so N2 and O2 at a really high temperature. This one here ends up forming 2NO gas. It ends up oxidizing. They used to think oxidation was, well, reacting with oxygen, gaining oxygen. That is one good way of looking at it, although in the next chapter we'll have to qualify that a little bit. What's going to happen here is we're going to look at how does this end up forming our NO2s before it actually runs into water. So what's going to happen is either the 2NO, it just oxidizes further and becomes 2NO2, or it could just be N2 reacting with oxygen in a slightly different ratio that ends up getting 2NO2. In both cases, we end up making NO2. And then what's the trouble with NO2 here? If you remember from our equilibrium chapter, we had started looking at like a N2O4 equilibrium with 2NO2. I don't know if you remember, NO2 was actually a brown colored gas. So what would end up happening is just having these NO2s, even forget about acid rain or whatever, this one here will end up forming a brown smog in our atmosphere. So not the greatest for our health. But more so what we're worried about here is the acid deposition. If we now take this NO2, regardless of how it's created, the NO2 running into water ends up forming combinations of nitric acid and nitrous acid. Again, it's a non-metal oxide. No real surprise, we end up forming acidic solutions. So nitrous acid, nitric 3 acid. We can also have other fancy equations as well. I would at least maybe memorize this one here so that you can note, well, it's a non-metal oxide. We potentially will make these acids here. There are other ones as well. I'm just going to give you one more. Let's say 4NO2 reacts with O2, reacts with water. This one here will end up becoming 4NO3, HNO3. And again, we'd ended up forming some acidic oxides. Okay. So the remaining of this lesson here, we're going to look at, all right, now because of these SOx and NOx, our rainwater is actually slightly acidic. What are some direct effects because of the rainwater? And then also let's take a look at what are some solutions, how can we address this environmental problem? So some effects on plant life here. Acids, their job is to donate protons. This one here will typically exchange with metal ions in soil. Same thing as start eating away limestone deposits here. It can take away important nutrients in the soil and cause these nutrients to actually run off from the soil, get washed down, and therefore the plants actually lose out on these nutrients. So that can have an impact. Acidic rain here can also cause a number of lakes to become fishless. So the pH of the water is a little bit too acidic for the fish to survive. So that can have a direct impact. Certain fish can't survive below a pH of 5. Rivers are pretty much dead at a pH of 4. So that could be a sort of direct consequence here. Remember what we're thinking here is pH of 7, right? That should be neutral at 25 degrees. Our rainwater is naturally acidic because of CO2. That's not called acid rain. It's called acid rain anything that's less than pH 5.6, and that's due to a bunch of these SOx and NOx. And that's when things really get very deadly for things. So acid rain lowers the pH of natural bodies of water, kills the organisms there. Sometimes aluminum ions get trapped in rocks, dissolved under acidic conditions. So rocks are, there's maybe many minerals or metal materials here. Basically, the acids eat away at the rock, and basically we're worried about this aluminum ion here. Aluminum actually starts interfering with fish scales and reduces their oxygen intake. I want to just remind you for the aluminum, it's a little bit weird to think about why is aluminum an acid? How could it actually release a proton? Remember, Al+3 doesn't exist as a single ion in solution. First thing is it has a very high charge, so it's not very soluble. But the other thing in solution is water. Water, again, is a ligand. Overall, it's a neutral molecule. I can point my oxygen end, and I can actually data bond to the aluminum here. So you just want to note down here, aluminum, other ions as well, Fe+3, chromium +3, these are very common ones. As they form data bonds here, I'll do it for aluminum. Aluminum gets surrounded by 6 waters. That's your most common geometry. Water does help to stabilize the charge, but being neutral, it can't get rid of the fact that aluminum is still a +3. This one here is actually a weak acid, so we see that from the equilibrium here. Basically, upon coordinate bonding and covalent bonding with the aluminum, I can start pulling off some of these other H's. And what we end up with here is an H+ ends up getting lost, and what's left over for my complex ion, aluminum still has maybe 5 waters. For the 1 water where I pulled out the H, there is now an OH. Because that H here is left with the H+, it's left its electron around. So this one here is now a +2. And this one here can subsequently, it can lose another H+. It can make water 4, OH. Let me just show that here. This one by itself can end up forming H+. Then we have aluminum, now only maybe with 4 waters left over, 2 OHs. Yes, these are OHs that I would need to be a base, but because they're now covalently bonded, I'm not going to lose those. So as I lose those 2 H's here, I'm going to now be a +1, and I'm probably going to do that just one more time, and then I end up with H+. I'm probably going to just stick around like this, water, 3, OH, 3, and now we're actually neutral. Right? So overall, aluminum, even though at first it didn't have the H+ to give up, it definitely does have, in this complex, H's. So back to some consequences there. The nitrates that are produced from nitric acid. So nitric acid is HNO3. When this gets bubbled into water, it ends up forming a whole bunch of different nitrates, NO3 minus compounds. Biologists like using the word here, can lead to eutrophication. And that's actually a situation where sometimes, not just the minerals are sort of leaving and the plants are dying off, sometimes the minerals build up in certain areas that the plant growth is actually too plentiful. And what's going to happen is we may have excessive plant growth, more than normal. And what's going to happen is there's going to be a lot more competition for the minerals. So very high oxygen demand. Right, so too much of a good thing is not good. Right? What about on materials here? On materials, especially building materials like marble and limestone, I already referred to. These ones here are calcium carbonate. They're essentially what our table chalk is made out of. Calcium carbonate. Calcium sulfate is actually more soluble than calcium carbonate. It's going to wash out of the limestone. So let me just show you some of these reactions here. Let's say we have CaCO3 as a solid. When this one here gets reacted with sulfuric acid, the sulfuric acid basically eats away at the calcium carbonate. It swaps places with the carbonate. We end up getting calcium sulfate, and we end up getting carbonic acid. Now, we had seen carbonic acid, it could do one of two things. It can act like an acid, and it can become H+, equilibrium with HCO3-. It can keep increasing the H+ supply, or it can actually decompose and actually end up forming CO2 and water and causing some sort of atmospheric problems as well. So, sort of two consequences there. The calcium carbonate gets swapped out for calcium sulfate because the calcium sulfate is more soluble. When rainwater runs off, it's going to taper off this calcium sulfate. We're going to end up getting holes inside our structures. Another common formula for you here. Let's take calcium carbonate. This is currently a solid. Let's react it just directly with the sulfur dioxide gases, oxygen gases here. This one here similarly ends up forming calcium sulfate, which will end up being aqueous and runs off, and then ends up releasing off more CO2. Okay. We can make one other note here while we're at it, talking about building materials here. Acid rain also increases metal corrosion. Right, so corrosion is a fancy word for rust. We're going to do this a little bit more in our redox chapter that's coming up. But basically, we're going to have, let's say, metals like iron in the presence of really strong acids like sulfuric acid, even though only the first protonation is acidic. It's a common property for acids that they basically react with metals. We're going to end up getting iron in the oxidized form, and then we're going to end up getting bubbles of hydrogen here if I did this experimentally here. And basically, as I start getting FeSO4, this one here is now an ionic compound. This one here enhances ionic conduction. We need to have charges, and we need them to be able to move around. In this case here, because there's more charges, it actually increases the rate of what's referred to as a redox reaction, oxidation reduction reaction, one losing electrons, one gaining electrons. We're going to study this a lot more in the next chapter, and the example is rusting. So that's your corrosion. Now, it's not all doom and gloom because we've studied redox reactions. Even though it's spontaneous, nobody wants it to occur, it's a very slow reaction. There are some ways we can actually protect things from rust. We'll see this more so in the next chapter. We can perform something referred to as cathodic protection. It has that root word there, cathode, and basically we're actually forcing the cathode here, force the Fe to stay reduced, force it into the stable no charge state. If iron is not allowed to become Fe plus 2 or plus 3, it won't actually be able to oxidize. Sometimes it actually involves cathodic protection, or sometimes called the sacrificial anode. If, let's say, iron is a very expensive metal, we can sacrifice something else. Again, the chemistry would say, maybe I have an iron pillar, I want to preserve this here. I might coat it with a sheet of aluminum. Both of these potentially can get oxidized. There's going to be a competition who oxidizes better. If aluminum oxidizes better, it's the aluminum that's going to rust, and the iron will be kept in this reduced state here, and therefore it's going to be kept from rust. It can be even a simple solution here. For rust, basically it needs to be exposed to sort of water and oxygen environment. You can just actually apply a paint layer. Paint is typically nonpolar here, and it's going to protect the metal surface from actually interacting, from colliding with the neighbors. The problem here is you might only have a tiny scratch on the paint, and already it's going to start rusting all over. Okay. On the last page here, what are acidic rain? What are some of the consequences here that might interfere with human health? In this case, nitric acid and sulfuric acid can irritate any mucous membranes, mucous linings in our body, and therefore it can cause increased respiratory illnesses. So that could be a direct consequence here. Acid rain also usually finds its way. Acid rain increases poisonous metal ions in pipes. So sometimes you hear about, oh, there's lead in the pipes, or there's other heavy metals. The concentration doesn't need to be that high for it to cause consequences here, and those minerals start leaching because the pipes sort of wear down because of acid rain. The last thing we're going to end off with today here is we're going to figure out, well, these are all the sort of, here's why we have acid rain, here are some of the consequences. What are some chemical solutions that we can to actually protect against acid rain? So there's actually sort of two main strategies here. The first strategy here is, let's just stop the acid rain. The acid rain has already formed. What can you do about it? So we can start at the source. Well, what's causing our acid rain? It's the SOx and NOx. Let's limit the SOx and NOx that we're actually throwing into the atmosphere. So that could be limiting our industrial processes, finding more efficient reactions here, or even if the reactions, we still have to do it, sometimes they engineer these chimney stacks with, sometimes they call them scrubbers. And basically it's a job of those scrubbers to actually force the SOx and NOx, instead of being vaporized and sort of put into the gas state, it's sort of collected before it actually leaches into the atmosphere. Because a lot of these industrial processes are energy sources, if we can trade in sort of these burning fossil fuels, energy sources, every time I can trade in for a more alternative energy source, I can still have the energy that I desire without the sort of consequence of polluting our atmosphere. So think about any alternative energy sources here. We can utilize solar energy more, electric photochemical cells. We can use wind energy with turbines. I can use tidal energy or water energy. I can use nuclear power for energy. Right. We've had lots of gains in alternative energy. The reason why we still heavily rely on fossil fuels is because they're relatively cheap, although we know it is a finite resource. We know it's not renewable, and this time we know our fossil fuels are actually causing these industrial problems. So use those things instead of fossil fuels. If you do the energy option, we're going to actually look at some of these reactions in a little more detail. The burning of coal, burning oil, burning methane, a primary component natural gas. Right. So if I can trade in for more alternative energies that are more environmentally friendly, why not? We can also, especially, again, the acid rain is already formed, right? We now have very acidic lakes and acidic bodies of water. What you can do is you can start throwing in metal oxides or metal hydroxides here. These ones here are directly add these bases to neutralize the acid. So let's say CaO, it reacts with sulfuric acid, and this one ends up becoming calcium sulfate and water. Pretty much here, the reason why a metal oxide, you may remember from your previous chapter, why are metal oxides basic? Metal oxides as ionic compounds, the CaO breaks up, it forms Ca plus 2, O minus 2, and we spent this chapter looking at O. Actually, this O minus 2 is actually a strong base. This one here, actually one-way arrows. It's going to react with water. I'll show you the reaction here again. We're going to do a lot of this in our organic chapter. We're going to see if you can tell me something about how the electrons move, you can sort of predict how the reaction is going to occur. Oxygen minus 2 is going to actually data bond. It's going to grab the H. The electrons end up going back on the OH. Color code this for you. This is a one-way arrow. This one ends up forming here. The oxygen has grabbed the H. As it grabbed it, it became an H+, so this is now going to be OH-, and we've actually formed another OH- here. So therefore, it's a one-way arrow, it's forming base. As long as I'm ionic, as long as water has no trouble separating positive from negative, it would be a basic solution. So that's a solution sort of after the acid rain has already formed. They will specifically ask you, well, what about, like, what else can I do? Like, I know burning these gases is producing the SOx and the NOx. What I can do to actually limit how much gas I'm actually producing. Pre-combustion methods, so before combustion or post-combustion methods here. Basically, pre-combustion, the process to reduce, if you can't eliminate it, or remove if you can. Reduce or remove the sulfur in coal before burning. Right? Again, coal is just a carbon source. Sulfur is a very common impurity. If I can take this coal, right, if I can sort of pull out all the sulfur in an environmental and economical way, then I don't have to burn the sulfurs, then I don't generate the SO2s. That is a pre-combustion method. So we'll see these reactions in the energy option if you do that option there. Sometimes we can just extract it as just elemental sulfur, as a sulfite, metal sulfite. So pulling the sulfur out of the carbon before you burn the coal. We can do a process called desulphurization. This one here is shorthanded HDS. And this one here involves, it's a catalytic process. Most of your industrial processes have catalysts involved because we want to get most bang for our buck. We want to have the reaction rate fast. Catalysts sometimes also control how the reaction occurs as well. So this is a catalytic process that removes sulfur from refined petroleum products. So not only are we burning natural gases, usually we burn petroleum products as well. If I can do those reactions and get rid of the sulfur before you burn it, then I don't even need the scrubbers to actually grab the SO2 afterwards. Usually it's sort of a combination of those things that can overall help. What about some post-combustion methods here? I'll just do one of them with you here. A post-combustion method, we can actually do something called a flue gas desulphurization. Again, all we're trying to do is we're trying to get rid of the sulfur before burning the coal or petroleum for energy. This one here, flue gas desulphurization, this can remove, it's found to get rid of up to 90% of SO2 in smokestacks before they get released into the atmosphere. Again, that's an after burning method. We purified all the sulfur as much as we could, and now some of it is still leaching out as SO2. So let me just show you these reactions here. Let's just take our calcium oxide again as a base. Let's react it with the SO2 that's already formed. This ends up forming calcium sulfite. That one there is actually a solid. Calcium carbonate reacts with SO2, becomes again calcium sulfide. I'm just emphasizing, notice that we're ending up forming solids, and because we're actually forming solids, these ones here can be collected up as deposits. They won't end up just leaching out to the environment. So this one here will end up producing CO2. And then we can take this calcium sulfate, it's already better because it's a solid. Calcium sulfite, solid, react with oxygen, and end up forming a neutral calcium sulfate. Again, the advantage again is this is solid, and this compound here is actually a neutral compound. This was the one from earlier. It was the problem. Oh, this one here is more soluble than calcium carbonates, but all we're trying to do here is we're trying to remove SO2 from the atmosphere before it actually leaches out there. Okay, so just have another look over this section here. Pretty much you need to know acid deposition could be like rainwater. It could be all these sorts of types here. Make sure you know it's because of SOx and NOx, and these are some methods that we can address it. Right? So if you have any problems, just let me know. Thanks, guys.